Hey, this is your video for Monday, Martin Luther King Day. This is actually example 16 on page 235. It is just wrapping up the tail end of that section we've been in. But I just thought, especially with most of you being seniors, this was really applicable because you might be making some rice. So these are the directions off of boxer rice. And we're going to assume that you don't want 2 servings. That's not quite enough, but you don't want 4 servings. You want 3. So that's what we're going to do. So what do you do if you want 3 servings? Well, you're going to notice that 3 is between 2 and 4. It's like halfway between 2 and 4. So how do we find how much water and rice to do? Well, we need halfway between those amounts. So what we're going to do is we'll do 2/3 cup plus 1 1/3 cup. We'll add them up and then we'll divide by 2, and that'll give us that average, that number right in the middle. So that's 2/3 plus 4/3, changing that mixed number to an improper fraction. That's 6/3 over 2. 6/3 is the same thing as 2. 2 divided by 2 is 1. So we need 1 cup of rice, and it was equal 1 cup of water. And then if you look at the salt, you need halfway between 1/4 and 1/2 of a teaspoon. We're going to do the same thing. We'll do 1/4 a teaspoon plus 1/2 a teaspoon, but divide it by 2. Add it up and divide by 2. We'll get a common denominator of 4 in the top. So we got to multiply by 2. So that's 3/4 divided by 2. Let's read it this way. That's 3/4 divided by 2. So we will keep the first one the same, change division to multiplication, and get the reciprocal of the second one. Keep change flip. So we're going to need 3/8 of a teaspoon of salt. Good luck finding that measurement. You might actually have a little measuring spoon that's 1/8. I think I have one in one of my sets, so you could do 3 of those. And then butter and margarine is nice. You need half of that, so that would just be 1 1/2. That's halfway between 1 and 2. But if you wanted to do it the way we're doing it, you would do 1 plus 2 divided by 2 is 3/2, and 3/2 is 1 1/2. I just thought that was nice for you all going off to college. Okay, now we'll go on to the next section, the irrational numbers. And all the numbers that we've studied so far in this class have been rational numbers. We started out with our natural numbers, and then we added 0 to it, and we had the whole numbers. Then we added the negatives, and we got the integers. And then we realized we could write all of those things as ratios, fractions, rationals. Well, there's a whole nother set of numbers that you can't write as fractions, and they're irrational numbers. A real number that cannot be written. As a ratio of 2 integers. So it can't be written as a fraction. So Pythagoras, I've got his little picture here. Interesting guy, but he found out with right triangles, he is credited for the Pythagorean theorem, a squared plus b squared equals c squared, where c has to be the hypotenuse. But he realized that if he had a square that was 1 unit by 1 unit, and he tried to figure out what the hypotenuse was, so he went about using his theorem. 1 plus 1 equals x squared. 2 equals x squared. Take your square root. There was not this didn't have a rational number answer. And I'm going to pull it up on my calculator real quick. So this is what the calculator on my phone got when I did the square root of 2. And it gave me all the way to 5 and so on. I know it doesn't stop. So he realized there was not a number times itself that I could get a 2. And that prompted the need for a whole new set of numbers, these irrational numbers. So what are irrational numbers? They are decimals that do not terminate or repeat. And a good way to find one is take the square root of a number that's not a perfect square, like 5, square root of 11, square root of 2 that we just did. Pi is an irrational number. It doesn't terminate, it doesn't repeat. The number e, if you find it on your calculator, it's an irrational number. So a whole group of numbers out there that don't terminate and don't repeat. So that brings us to square roots, and we have a square root symbol, which is called the radical sign, and the number under the square root is called the radicand. And we're going to talk about just perfect squares. So we'll have a number, and then that number squared. It's called a perfect square. I am going to go ahead and make a kind of long chart. So 1 squared is 1 times 1, which is 1. 2 squared is 2 times 2, which is 4. 3, perfect square is 9. 4 is 16. You know a lot of these. You used them a lot in geometry. In fact, I think I had us go up to 20. You might just make a little running list of these down the column of your paper because they're handy to try to memorize and use. So that's my list of perfect squares to 20. And we're going to practice simplifying radicals. So the product rule for radicals. If you have a square root of a product, then you can separate that as the square root of one of the numbers times the square root of the others. As long as a is greater than or equal to 0 and b is greater than or equal to 0. So, for example, if you've got the square root of 25, it's on that list of perfect squares. So its answer is just 5. If it's on our perfect square list, then it is a rational answer. But if it's something like the square root of 18, then you're going to maybe try to break it down to 2 and 9. And you maybe say that's the same thing as 2 times the square root of 9. Square root of 2, I can't simplify, but the square root of 9 is 3. So that becomes 3 square root of 2. It's not quite the way we did it in geometry. We broke it down with factor trees to primes. And we knew we were looking at a square root with an index of a 2. So we were looking for a pair of numbers. And the pair got to come outside and the other number had to stay underneath. So maybe that is kind of similar or familiar to you. B part, we'll do square root of 80. you can try to think of perfect square factors. I'm not so great at this always. And then break it down to square roots of those factors. 16 is a perfect square. 5 is not. So your answer is 4 square root of 5. But you can do it the way we used to do it. 8 times 10. Break 8 down. Break 4 down. Break 10 down. And remember, this is a square root, so we're looking for groups of 2 of the same thing. There's a group of 2 and there's a group of 2. So this group becomes this. This group gets to come out for this. But that 5 has to stay underneath by itself. So it is 4 square root of 5. So the rule for adding and subtracting radicals, kind of like the rule for adding and subtracting fractions. Do you remember on fractions we needed a common denominator? We just did this today. Then we could add those numerators and keep that denominator. So it's kind of similar to that. The rule for adding and subtracting radicals is you need a common radicand. So if the number under the radical is the same, then you can just add those numbers in front, and it's that square root of c. So, example, if you have 5 square root of 3 plus 7 square root of 3, and your square roots of 3 are the same, then all you have to do is add the 5 and the 7. The problem, of course, comes when they don't match. You've got like, you make sure they do it for you. Let's say you had 5 square root of 3 minus the square root of 12. These aren't the same. So I don't just immediately get to stop. I've got to see, can I simplify? We'll check on this one. I cannot simplify 3. It's prime. But I can simplify square root of 12. 2 and 6 and 2 and 3. So square root of 12 is the same thing as 2 square root of 3. So now this problem is 5 square root of 3 minus 2 square root of 3. Now your radicals are the same. So you subtract and you get 3 square root of 3. Okay, to multiply radicals, I think it again has a close connection to multiplying fractions. When we multiplied fractions today, we did not have to do anything special. All we did was multiply the numerators and we multiplied the denominators. We didn't need common denominators. We didn't have to do any work with it at all. The same is kind of true for multiplying radicals. Let's say you have 2 square root of 5 times 3 square root of 8. Well, all you have to do is multiply the numbers outside the radical, the coefficients together, and then you multiply the numbers under the radical together. Then you do have to check if 40 breaks down. Well, I just multiplied 5 and 8 and got 40. 8 is 2 and 4. 4 is 2 and 2. So that's 2 square root of 10. Well, I already had a 6 out front. And square root of 40 broke down to 2 square root of 10. So it's 6 times 2 square root of 10, or 12 square root of 10. Last thing for today is dividing radicals. If you have square root of a over the square root of b, I can put those both under the same radical. And that is legal. And sometimes it's easier to work. So for example, a, if we've got the square root of 75 over the square root of 3, we're allowed to put them under the same radical and then go ahead and divide underneath that radical and then take the square root. Oh, it's a perfect square. We would have gotten the same thing had we simplified it. Let's say we wanted to break 75 down. It's 3 and 25, and 5 and 5. So it's a pair of 5s with the 3 left over. So I could rewrite it that way. And then these square roots of 3's cancel, one on the top and one at the bottom. They divide out, and I get 5. All right, last one. Square root of 60 over the square root of 5. I'm allowed to put those both under the same radical. 60 divided by 5 is 12. And then let's break 12 down as a pair of 2's with a 3 left over.